Welcome dear students. So today we will start error coding in your digital communications module. So let's begin. So so in error coding, basically what we do is that we, apart from the actual data bits, okay, you introduce some redundancy or some extra check bits. Okay, so the role of this check bits is basically to detect an error and at some instances to detect the error as well as to correct the error. So you have learned so far in your digital communication module about how to design a receiver which is optimum in nature, or in other words, a receiver that minimizes the probability of error. Okay, however, you cannot have zero error. Okay, so there will be some error, however small they are, and if you introduce error coding, then you can design a system which is near perfect. So first you design a receiver which is optimum and reduces the probability of error, and then on top of that, if you introduce error coding, then you can even detect whatever few errors you have, and then an even better system can also not only detect but also correct the errors. Okay, so we will learn the concepts of error coding in this lecture and the next lecture videos. So let's start. So for a transmitter, a given frame contains an error detecting code or check bits, and those check bits are actually calculated from your data bits itself. Okay, so the check bits are some function of the data bits. Okay, so check bits are some function of the actual data bits within a frame. Okay, and the check bits are appended to the data bits. In the receiver, the receiver separates the incoming frame into the data bits and the check bits, and then calculates the check bits from the received data bits. So as you see, the check bits are a function of data bits. So when the receiver receives the data bits, it tries to calculate the same function. Okay, it tries to calculate the same function of the data bits that it has separated, and then whatever the calculated check bits are, they compare the calculated check bits against the received check bits. Okay, so there is the actual received check bits and then the calculated check bits from the received data bits, and then these two are compared. If they mismatch, then there is an error that is detected. Okay, so schematically this is what happens. So you have the data bits, you have k data bits, and then you calculate your check bits from those data bit by performing some function, and then you append those check bits to your data frame, so that the total frame length is n bits. So therefore you have n minus k check bits, and then these are transmitted, and in the receiver you are receiving the data prime, which is the received data. This might contain some error because of noise and other channel impairments. So you calculate, you first separate the data and the check bits, and then calculate a function f, the same function f that was here of the data, received data, and then you compare them together. If they do not match, then there is an error and you can detect that error. Okay. So talking about that function of the data bits, so it can be any function. So it can be, let's say, a parity type of function. So in the parity check, what happens is that the parity bit is appended to the block of data, and let's say you have one parity bit. So this is your check bit actually, and that bit, let's say the function here is that the entire frame should have an even number of ones. Okay, so this is your function f. Okay, so you check the data bits. So these are your data bits, let's say a 7-bit character, and you have how many ones here? 1 2 3 4. So if your parity is an even parity, then you append a 0 here, so that the total number of ones still remain even. If you follow a odd parity, then you append a 1 here to make the total number of ones as odd. Okay, so the function f is basically checking the total number of ones, okay, and ensuring that either it's even or odd. Okay, so in this case, for even parity, the function is ensuring if the total number of ones is even. In case of odd parity, the function is checking if the total number of ones is odd. Okay, so this is a function of the data bits as per the general theory of check bits. So another type of error detecting codes are cyclic redundancy check codes. So for cyclic redundancy check, in the transmitter you have a k bit block, and the transmitter generates an n minus k bit frame check sequence. Okay, so you have k bits, and then you have n minus k, so the total is n. Okay, so this frame size is n, and this n minus k is the frame check sequence. Okay, so in case of cyclic redundancy code, the check bits that are here, the n minus k check bits, are called frame check sequence. Okay, this is a term which is particular to cyclic redundancy code. Okay, so in the receiver divides the incoming frame by a predetermined number. Okay, so I will come to this later. What is this predetermined number? So let's assume that they have a predetermined number, and the receiver divides the incoming frame by this number, and the rule is that if there is no remainder after this division, then there is no error. Okay, but if there is a non-zero remainder, then there is an error. Okay, so that's the error detection rule for cyclic redundancy check. Okay, so you can represent cyclic redundancy check using modulo 2 arithmetic. So modulo 2 addition, okay, is nothing but the exclusive OR operation. Okay, so this is your modulo 2 addition. Okay, so let's look into the different parameters of CRC first. So let's say T is the n bit frame to be transmitted. Okay, and D is the k bit data block. Okay, so this is the first k bits of T. Okay, and F is the n minus k bit frame check sequence. So this is the last n minus k bits of T. So you have T as the entire frame, and D is the data block, and F is the frame check sequence. Okay, and then this is the first k bit, and then this is the last n minus k bits. Okay, and P, let's say this is the pattern of n minus k plus 1 bits, which is the predetermined divisor. Okay, and let's say Q is the quotient and R is the remainder. Okay, so if you move on with these assumptions, so let's say t divided by p, let's do this operation. So in the receiver, this entire frame t is divided by p. Okay, so for t divided by p to have no remainder, let's say we start with this. So this is basically the representation of t in modulo 2 arithmetic. So if you multiply by 2 to the power n minus k, so this means that there is a n minus k bit shift to the right. Okay, so basically 2 to the power n minus k times d plus f actually means this thing which we showed. So this is the k bits data, and this is the n minus k bit frame check sequence. So this is t. So the total frame is this plus this. So this is how it is represented in modulo 2 operation. Okay, so now if you divide 2 to the power n minus k times d by p, just this part, okay, just this part, then let's say you have a quotient and a remainder r. Okay, now if you use the remainder as your FCS or the frame check sequence, okay, so let's say if you use this r, or let's say if you set f is equal to r, okay, then you get this. Okay, so instead of, let's say 2 to the power n minus k times d plus f, we are writing 2 to the power n minus k times d plus r. Okay, so basically the frame check sequence is set to the remainder after dividing 2 to the power n minus k times d by p. Okay, so if we do that, then what happens? If you do that and then you divide t by p, then you will have this thing. So 2 to the power n minus k times d by p and r by p. Okay, now let's say 2 to the power n minus k times d by p is basically this quotient plus this remainder, right, according to this expression. Okay, so if you set this part with this, then you will have t over p is equal to q plus r over p plus r over p. So now in modulo 2 arithmetic, if you are adding twice the same term, or let's say an exclusive OR, so remember this plus is an exclusive OR or a modulo 2 addition. So if you do an exclusive OR of a bit with itself, it will give you 0. Okay, so basically if you are doing this operation, then this will give you a 0 in modulo 2 arithmetic, provided that this plus is a modulo 2 addition, and you will get q without any remainder. So therefore t is exactly divisible by p if you set t equal to 2 to the power n minus k times d plus r, where r is the remainder when you do this. Okay, so if you set your frame check sequence equal to r, where r is the remainder when you divide 2 to the power n minus k times d by p, then your entire frame t is exactly divisible by p. Okay, so that is what is done in CRC. So you set the frame check sequence equal to r, where r is the remainder when you do this operation. Okay, so now let's look into an example. Okay, So let's say your message is 10 bits, okay, and your pattern is this 6 bits, okay. So this is basically n minus k plus 1 bits, okay. So this is your k, and FCS or the R is to be calculated. So this is 5 bits. So this is basically n minus k bits, okay. So therefore your n is 15, your k is 10, and n minus k is 5, okay. So the first thing you do is to shift your message towards right, okay, by multiplying it with 2 to the power n minus k. Here your n minus k is 5, so you are multiplying with 2 to the power 5. So if you multiply this d with 2 to the power 5, it's basically a right shift, okay. So now it reads like the same d with 5 zeros appended here, okay. So this is basically a right shift, or rather a left shift, okay. Depends on which side you are looking. So let's say a left shift, okay. So now if you divide this 2 to the power n minus k d with p, then you will have this quotient q and this remainder r, okay, 0 1 1 1 0. So if the remainder is now added to 2 to the power 5 times d, then you will get t, which is now the original message, and then whatever is the remainder that you got, 0 1 1 1 0, okay. So this is the entire frame that you need to transmit. Now if there are no errors, the receiver receives t intact. So the received frame is divided by p, and you see that you get a 0 remainder, and because there is no remainder, it is assumed that there have been no errors, okay. So this is how cyclic redundancy check operates. If there were an error, you can check it yourself. Just flip any bit on the D part of the message, okay. Just flip any bit within this part, okay, and then see if you do the division, you will get a non-zero remainder. So we can express CRC using polynomials also. So all values are expressed as a power of a dummy variable x. So you can now do the same operation. So you can say that D, your message, is a function of x, okay, and you can write D as whichever value has 1, you have the power of x present in the polynomial, and whichever value is 0, that power of x is suppressed, okay. So you can write the message as a polynomial of x, like x to the power n plus x to the power n minus 1 and so on, okay. So if you don't have this particular bit, if this bit is 0, then this term is suppressed, okay. If this bit is 1, then this term remains here. So that's how you represent using a polynomial. And then in the polynomial form, if you have x to the power n minus k multiplied with the actual polynomial, so this represent a shift similar to the multiplication of 2 to the power n minus k, and then everything is represented in polynomial form. So if you divide by the predetermined divisor px, then you have the quotient and the remainder, and then if you use this remainder as your frame check sequence, then the entire message would look like this. So let's check with an example. So let's say if this is your D, the same D as before, okay. So this can be represented like this, as I was saying, okay. So so you have if you read from this side, so 0 1 2 3 4 5 6 7 8 9. Okay, so x to the power 0 is present, so this is 1. Then x to the power 1 is missing, then x to the power 2 and x to the power 3 are present, so x to the power 2 and x to the power 3 are here. Everything else is 0. Then x to the power 7 is present, so x to the power 7, and then x to the power 9 is here. Okay, so this is the polynomial form, and for the p we have this. Okay, now we should end up with r equal to 0 1 1 0, which corresponds to this. Okay, so let's see if that is the case. Okay, so this is the shifted version of the original message. Okay, so this is x to the power 5 times dx. Okay, so if you divide this with the px, then you will get the remainder, which is x to the power 3 plus x square plus x. Okay, so this indeed is the case, and this correspond to 0 1 1 1 0. Okay, so this is a circuit that can emulate this CRC frame generation. Okay, so let's say the first 10 bits, which are the message bits, so let's say for the D part. Okay, so those are the first 10 bits. So we are still looking into the example, this example. Okay, so to generate the T corresponding to this example, we need to have a circuit like this. Okay, so this D is the first 10 bits. Okay, and then the next 5 bits is R, and then T will have total 15 bits. Okay, so the first 10 bits, when we were trying to generate the first 10 bits, the switch 1 is in position A and switch 2 is also in position A. Okay, so the first 10 bits of the message D was actually, let's say, 1 0 1 0 0, so 1 0 1 0 0 0 and 1 1 0 1. So this is your input. Okay, I. Okay, so you can see your input is 1 0 1 according to this. Okay, and then this is the first 10 bits. Okay, so when this is going through this circuit, okay, then you are having how many exclusive ORs? 3 exclusive ORs. Okay, so this exclusive OR is this one is basically, so here is your input I. Okay, so here you will have C4 exclusive OR I at this point. Okay, so here at this point you will have C4 plus C1 plus I. Okay, so C4 plus I is here, C4 plus C1 plus I is here. Okay, and at this point you will have C3 plus C4 plus I. Okay, so this is the output here, so this is here. So if your I is this, okay, and your, let's assume that initially your C4 C3 C2 C1 C0 are all zeros, then if your I is this, then the first few outputs will be like 1 1 1. So C4 C3 plus I will be 1, C4 C1 I will be 1, and C4 I will be 1. Okay, now in next step, okay, so whatever is coming here, okay, is also getting as the output. Okay, so this input, the first 10 bit is also the output. Okay, now after the 10th step, so these are the steps. Okay, because of this shift, the circuit is changing. The contents of the shift registers are changing, and you are getting the output according to this exclusive OR. So at the first 10 steps, you will get as the output here all the first 10 bits of the message. Okay, and then after the 10th step, this switch shifts to this point B, and this circuit breaks. Okay, so this also goes to point B, which is a floating point. Okay, so if that happens, then whatever is the state of the shift register at the 10th step, so this is 0 1 1 1 0. Okay, so this is 0 1 1 1 sorry 0 1 1 1 and 0. Okay, so if this switch is closed and this switch is open, then this exclusive ORs doesn't work anymore. This entire chain now works as a simple shift register. So now the output will be in step 11 the output will be 0, the step 12 the output will be 1, step 13 the output will be 1, step 14 the output will be 1, and step 15 the output will be 0. So that means from 1 to 10 you will have these numbers, and from 11 to 15 you will have 0 1 1 1 0. So now if you append this and this, the total message is basically this entire 15 bits. So 1 0 1 0 0 0 1 1 0 1 and then 0 1 1 1 0. So this part comes at the last 5 bits, and this actually is the remainder or the frame check sequence that you had here. Okay, so this is how this circuit works. So this entire circuit, after the 15 steps, there are the 10 steps shown here. 11 to 15 will be these frame check sequence numbers. So this circuit will generate the entire 15 bits of the total frame. So for this particular example that we took up, this is the circuit that you have. Okay, so you can generate CRC. I mean, you can generate an entire message frame according to CRC, like this. Okay, so we will move on now. So let's move on to block error correction codes. So in the transmitter, the forward error correction encoder maps each of the k bit block into an n bit block code word. Okay, so here things are little different. It's not just appending the n minus k bits at the end to make it a total n bit. Here the k bit block is mapped into a n bit block code word using a forward error correction encoder. Okay, and then this code word is transmitted along the channel, and at the receiver the incoming signal is demodulated, and then the block is passed through an FEC decoder to get back the k bit block. Okay, so schematically this looks like this. So the entire k bit data block is mapped through a FEC decoder into a n bit code word, and that is transmitted. And when you receive the same code word, that might be affected by noise or the other channel impairments, so you denote it as code word prime, and then you do the FEC decoder, which is the exact inverse mapping of this encoder, and then you get back the data. If you have no error or correctable errors, then you get back the data, but sometimes you detect the error but you cannot correct it. So in that case you just indicate that there is an error. So as I was saying, so FEC decoder can have different outcomes. So there could be no errors present, so this is the best case. So the code word produced by decoder matches the original code word. But then the decoder can detect error and correct those errors as well. The decoder detects but cannot correct bit errors. It only reports uncorrectable error. It can also sometimes incorrectly correct bit errors. Okay, so in that case the error pattern looks like a different block of data sent. Okay, so that can be also possible. And finally the decoder detects no bit errors. This is also possible though errors are present. Okay, so these are the different outcomes of the FEC decoder. Now let's move on with the block code principles. So the first thing is the Hamming distance. So for two n-bit binary sequences, the number of different bits that they have is called the Hamming distance. So in this example, V1 and V2, you have the Hamming distance equal to 3, because this bit is different. And then what else? This bit is different. Okay, and then this bit is different. So the total 3 bits are different. So Hamming distance is 3. The redundancy is the ratio of the redundant bits to the data bits. Okay, so the k bits of data are there, and then the n minus k bits that you have in the final block, though they are the redundant bits. So basically this ratio n minus k over k is defined as the redundancy. The code rate is the ratio of the data bits to total bits. Okay, so this is basically k over n. And the coding gain is the reduction in the required EB by n0 to achieve a specified bit error rate of an error correcting coded system. So this is called coding gain. Okay, so if you do coding and then plot the BER for EB by n0, so let's say this is, let's say, without coding. And this will be, let's say, with coding. Okay, because with coding you have less number of errors. Okay, or rather the receiver can correct the errors. Okay, even if they have. So basically, let's say for the same BER, let's say this point is 10 minus 4. So to obtain 10 minus 4 without coding, you spend more energy. So the EB by n0 is more than with coding. Okay, so this part in dB is your coding gain. Okay, this is the gain that you have in signal to noise ratio because you are performing coding. So let's look into the decoding process for block code. So let's say you have data blocks. Okay, so let's consider that your data block is 2 bits. So k is 2 here. Okay, so you have all these 4 possibilities of 2-bit data, and then we have the corresponding code words which are 5 bits. So your n is 5. Okay, now let's say you receive this 00010. So this doesn't match with any of the code words. Okay, so therefore this is not a valid code word, and therefore an error is there. Okay, now if you want to correct this error, you check the Hamming distances. Okay, so this is basically 1 bit away from the first code word, 2 bits away from the second code word, 3 bits away from the third code word, and 4 bits away from the fourth code word. So most likely this was sent. Okay, assume that this was the data. So since the received code word is closest to this, you are assuming that this particular code word was sent, and this particular code word corresponds to this data block, so you assume that this data was sent. Okay, now let's say if you have a received code word like this, then there is a difficulty in correcting the errors. Okay, so this is 2 bits from this code word and 2 bits from this code word, and no other codes are closer, so you cannot decode, or you can only know that bit errors are there. Okay, but you don't know that which code word was sent because there is a tie here. Okay, so to actually handle the situation that you saw before, your code words should be very efficient. Okay, and the efficiency of a code depends on these parameters of n and k. Okay, so one family of codes are called Hamming codes. These are basically block error correcting codes with these parameters. So you have the block length equal to n, and the number of data bits is k, and the number of check bits is n minus k, and you have d mean equal to 3. Okay, so d mean equal to 3 means if you have, let's say, the block length of n. Okay, so basically the total number of code words possible is 2 to the power n, right? So if you go back to this example, sorry, if you have the message is k bit long, so the total number of code words is 2 to the power k. Okay, so basically if you have a k bit data block, then 2 to the power k code words are possible. Okay, each of length n. Okay, so now if you look up all these 2 to the power k code words, okay, let's say in this case we have 2 to the power 2 because your k was 2, so you have 4 code words. If you look into all these code words and calculate the individual Hamming distances, so for example between these two the Hamming distance is 3, between these two the Hamming distance is 4, between these two the Hamming distance is 3 again. Okay, so if you just calculate the pairwise Hamming distances and then find out the minimum from this set, that is basically your d mean. Okay, so d mean is also a parameter of the code, and Hamming codes are generated for a d mean of 3. Okay, and the Hamming codes are called single error correcting code actually, or more precisely they are single error correcting, double error detecting codes, and this means that any of the family of Hamming codes can detect one error. Okay, detect one error and detect 2 errors, because double error detecting, and correct one error. And this property, detecting two errors and correcting one error, has to do with this d mean. Okay. So if your d mean is 3, then you can detect two errors and correct one error. So there is a relationship between these two. Okay. Now I want you to find out what is the relationship. Okay. After this lecture, go and check the book. Okay. And find out, and you can also look up into the internet and find out what is the relation between d mean and the error detecting and error correcting capability of the code with d mean. Okay. And then we will discuss this later in a discussion session. Okay. So to so what happens with the Hamming code? So you have k data bits and n minus k check bits. That is true for any block code. And then the decoding compares the received n minus k bits with the calculated n minus k bits using XOR. Okay. So basically you are XORing the received n minus k bits with the calculated n minus k bits. Okay. And this results in a n minus k bits, which is called the syndrome word. Okay. So syndrome word or syndrome is basically the exclusive OR of the calculated check bits, exclusive OR, the detected or received, received check bits. Okay. So the syndrome will be n minus k bits also, and the syndrome range is between 0 to 2 to the power n minus k minus 1. Okay. And each bit of syndrome indicates a match or a conflict. Okay, in that bit position. Okay. So if the syndrome is, let's say, 3 bits, okay, then the syndrome can be between 0 to 7. Okay. So this will be like 0 0 0 to 1 1 1. Okay. And each bit of the syndrome indicates a match or a conflict. Okay, in that position. Okay. So if the syndrome is all 0, then there is a full match. Okay. If the syndrome has a 1 in a particular position, then that particular bit is in error. Okay. However, you can see that there are some bits which have multiple ones. Let's say this 1 1 1. Okay. So in that case, the rule is different. Okay. So let's look into the rule. Okay. So for convenience, we want to generate a syndrome with the following characteristics. So if the syndrome contains all 0, then there is no error. If the syndrome contains only one bit set to 1, then there was an error in the check bits and no correction is needed. Okay. So the check bit, if there is an error in the check bits, then you don't bother. If the syndrome has more than one bit set to 1, then the numerical value of the syndrome indicates the position of the data bit in error. Okay. And we invert the data bit to correct it. Okay. So let's say if we have n minus k equal to 3, then the syndrome can be anything between 0 0 0 to 1 1 1, right? So these will be the all possible syndromes. So if the syndrome contains all zeros, then no error. So this is the no error. Okay. If the syndrome contains only one bit set to 1, then there was an error in the check bits and no correction is needed. So this is the case. This. Okay, so this is error in check bits. Okay, these are the cases where you have error in check bits. Okay, for the other cases, when the syndrome has more than one bit set to 1, so for example this one 0 1 1 means the third bit in the data has an error. 101 means the fifth bit in the data is in error. This means the sixth bit in the data is in error, and this means the seventh bit in the data is in error. Okay, so you have to generate a syndrome which has the following characteristics, and to achieve the above goals you have to follow these steps to generate the code. Okay, so you will go through these steps, but I will explain this with an example. Okay, so I will, and this is what happens in the receiver. So I will go straight to this example to explain how the Hamming code is generated. So let's say we want to compute a 12-8 Hamming code for this particular data. Okay, so these are 8 bits. This is the data part. Okay, this is the K part and this is the N part. So every Hamming code is characterized with NK. So here N is 12 and K is 8, and therefore the data contains 8 bits. Okay, and this has to be transmitted. Okay, and if the received block is this, find out if there has been an error, and if the error exists, can you tell if it is correctable and where its position is. So first look into the data and let's see how the data, how the Hamming code encoder generates the entire n bit frame from this k bits of data. Okay, so these steps are given here, but we will go through these steps through this example. So let's say eventually we need to have 12 bits. So let's say we have these bit positions numbered like this 1 to 12. Okay, and we also have this position written in binary. Okay, so this is corresponding to 1, this is corresponding to 2, this is 3, and so on up to 12. Okay, and we have the check bits. So the check bits positions are at location 2 to the power 0. So we will have 4 check bits, right? We have 8 data bits and the final frame is 12 bits. So we have n minus k equal to 4. Okay, so the check bits position will be in 2 to the power 0, 2 to the power 1, 2 to the power 2 and 2 to the power 3. Okay, in this way. So 2 to the power 0 is the first position, so we have a check bit here. 2 to the power 1 is the second position, so we have a check bit here. So C1, C2, then we have C4 here at the fourth position and C8 here at the 8th position. So we call the check bits by C, and this number indicates that which position they are in. So the check bits are in 1, 2, 4 and 8, these positions. Okay, so this is by rule. Okay, the check bits has to be in these positions in the powers of 2, and all this we are doing because we need to have a syndrome that has the properties that we talked here. Okay, the syndrome has to have these properties, and because of that we need to generate a code that follows these steps. Okay, so the check bits are inserted at positions that are powers of 2. Okay, so that's what we are doing here. So C1, C2, C4 and C8. All right, now the rest are the data bits. Okay, so D1, so C1, C2 has been taken by the first and second position, so the data starts from here, from the third placeholder. So here you have D1, then you have D2, D3, D4 and D5, D6, D7, D8. Okay. So wherever the empty locations apart from the check bits, okay. So the check bits are placed at powers of 2 and the remaining empty locations will be taken by the data bits from this direction to this direction. Okay. So there, following that rule, D1 comes at the third position, D2 is here, D3 is here, D4 is here, D5, D6, D7, D8. So we have all the 12 positions filled up. Okay. Now let's look into the positions which have 1. Okay. So the data is 1 at this position, and if you look here, then the data is 1 0 0 1 1 1 0 0. So these are the positions where the data is 1. Okay. So we are interested in the place value of the positions where the data is 1. Okay. So we write them here like this. Okay. So these are basically the positions where the data is 1, and if you do an exclusive OR of all these 4-bit numbers that correspond to the place holder where the data is 1, then you get the 4 bits of the check bits. Okay. So the check bits are basically C1, C2, C4 and C8, right? So if you do an exclusive OR of all these numbers, which are basically the placeholder values where the data is 1, then you will get 4 bits which are the check bits. Okay. So this is how it works. So the 10th position in the data is 1, the 9th position is 1, the 7th is 1 and the 3rd is 1. So if you do an exclusive OR of all these, you will get 0 1 1 1, and these are your check bits. Okay. So this is basically your C8 is 0, your C4 is 1, your C2 is 1 and your C1 is 1. Okay. So that's the entire block from here to here of 12 bits that you are transmitting, where your C1, C2, C4, C8 resides in the first, second, fourth and 8th position, and everything else is data. So you can see that the check bits are hidden within the entire frame. Okay. They are not just appended at the end. Okay. So now at the receiver, let's say you are receiving this entire block, but let's say one of the bits are in error. Okay. This bit initially was 0, now it is 1. Okay. After propagating through the channel. Okay. So now how will you detect this error and correct it? Okay. So let's say the Hamming code for this was 0 1 1 1. So these were the check bits. Okay. These were the check bits that we calculated in the previous example. 0 1 1 1 is the Hamming code. Okay. And then we look into the received frame and we just collect the positions where it is 1. Okay. So it is 1 in the 10th position. So we have 1 0 1 0 here. We have 1 in the 9th position. So we have this. We have 1 in the 7th position. So we have this. We have a 1 in the 6th position. This was originally 0, but after reception this is in error. So we are counting this. And then we have 1 in the 3rd position here. So now if you do an exclusive OR of all these, whatever positions that the data was 1 and with the Hamming code, then you get 0 1 1 0. So this is your syndrome basically, and you can see this correspond to the number 6 0 1 1 0. So the sixth bit is in error, so we can detect the error and then we can just flip this bit to 0 to just correct it. Okay, so I will stop here today and I will follow the remainder of the error correcting codes in the next video lecture. Thank you.